Thanks a lot for the opportunity to speak here. Yes, I'll be talking about using modular theory to constrain correlation functions of quantum field theory. What I'll mostly be talking about just as a proof of principle that you could use the inequalities, monotonicity of relative modular operator, one inequality that exists in modular theory, to extract certain inequalities in correlation functions. So these, the ones that I'm going to tell you might not be the most interesting inequalities, but there were just some inequalities that I found, and we can discuss this. So I'll try to reverse the logic, go from the end to the beginning. So I'll start with the inequality, and then we go back to the formal stuff. Everything I say appears in here. So the part one, so there are three parts to the story. In part one, I'll just talk about what is the inequality that we're finding. So inequalities for correlation functions of quantum field theory. I'll be talking mostly in terms of Euclidean correlation functions. So let's start with an inequality that you guys know, everybody knows. Well, actually, let me start over here. So consider a 4-point function. So some operator phi, the phi star, with some distance a. So these are 2 points. I'm going to take this. This is Euclidean sheet. I'm going to take this copied over here with the star. So I flip the stars. So if they are real, it's just a simple copy. And then I put them at some distance 2x. This is a 4-point function, right? And let's see what we know about this 4-point function. So for simplicity, take these guys to be scalar fields, so scalar operators. So what is this guy? This is, I'm just going to write it this way. I'll not put the stars, but there should be stars. It's just too much to keep track of. So first of all, we know that this is non-negative. Why is that? It's just a simple consequence of reflection positivity. I can draw a line here. And a reflection around this tells you that you could understand this state as an overlap. Sorry, as a norm of a state. So positivity is the first property. The second property, you know this, is that it's monotonicity. Monotonicity. Meaning that if I keep the distance of these pairs, a, and just separate them in x, just pull them apart, the first derivative in x has to be non-positive. Why is that? Because the first derivative in x could be understood as inserting p of x here, which after I continue to Lorentzian signature, this is just the Hamiltonian. And this is the, oh, I'm sorry, with a minus sign. With a minus sign, so this becomes, Hamiltonian is a positive operator, so this becomes, this has a fixed sign. So instead of a translation in x, I could pick, which was a killing vector, I could pick another killing vector, which is some sort of, it could be a null translation killing vector. So I'm thinking of analytically continuing these correlators in space-time. So instead of del x, I'll be talking about del u. And then I can just replace the same thing by del u of the correlator being equal to this time pu, which is also another positive operator, so it has a fixed sign. One comment is that, so you probably, so I'm using the fact that this is a killing vector. Therefore, the charge I'm talking about is a topological charge. So I can just freely, if I have an operator like this, and I'm writing the integral of the charge as an integral over this surface, I can move this around and write it like this, if there are no other insertions around. But it will not play a big role, but I just wanted to mention that. Then you might ask about higher derivatives. OK. So if you look at del x to the power of n or del u to the power of n, well, again, it's the same story. With a minus 1 to the power of n of a positive operator, pu or px to the power of n. So it has a fixed sign. Good. So these are the inequalities that you guys, well, we know from reflection positivity and positivity of h or pu. So now let's, I wish I'd used my space better. Anyway. So now let's look at a generalization of this. So what is the generalization that I have in mind? Here I just took this pair, and I copied it over here. I'm just going to split the space into 3 pieces. So this is 2 pi over 3, 2 pi over 3, and 2 pi over 3. And I'm just going to copy it like this. OK? So let's see whether these properties are satisfied. So the first one, positivity, is clearly satisfied because I can look at reflection positivity around this cut. But monotonicity is somewhat strange. Oops, sorry, 4, 6. So monotonicity, if I'm just first, let's think about shift in x. So what is shift in x? I'm taking these guys. So this is x, sorry. So this is x, and this is x. And the distance between them are kept fixed. So what I'm doing is that I'm taking these pairs and separating them. So this cannot be under. So what this is, and this using the same language, it's like an off-diagonal matrix element of Hamiltonian, which need not have a fixed sign. But I'll use quantum information theory to show that this is actually has a fixed sign. This is non-negative. So this is, we're going to use quantum information theory to show this. And a generalization of this for n, as the angle of this is 2 pi over n, and you rotate this n times, and you get to 1-point function. This is going to be a consequence of monotonicity equations that we find in modular theory. So how about the higher derivatives? So here's a conjecture. The conjecture is that for all these 1-point functions with particularly fixed geometry, with this particular geometry, this is going to be non-negative. And this does not follow from anything in monotonicity that we will discuss, but it's a conjecture that passes all the simple tests you could do in free field theories or conformal perturbation theory. And it's to be understood, I'll argue that this is to be understood as a generalization of QNEC. All right.
When you took the first derivative with respect to x, were you just changing that x?
Because of the symmetry, I'm changing all of the x's, but this is like 3 times changing 1. Or n times. Yep.
The conjecture that you have for the second derivative of u, is that specific for u instead of x?
So let's say yes. So for all the examples I tested, x also passes it, but there are extra terms in x. So this is safer to conjecture. But it would be more appropriate if it's a generalization of QNEC. All right, so let's try to see what this monotonicity is. So clearly, as I separate these guys and pull them apart all the way to infinity, clustering tells you that this 2-n-point function, oh, let me write it here. This 2-n-point function with a particular geometry we've been looking at clusters, so it becomes just 5 to the power of n. So if I look at this quantity and calculate its log, this is non-negative from just from monotonicity. This is non-negative. And it's conventional. If you want this quantity to be non-trivial as n goes to 1, you can divide it by 1 over n minus 1 and construct this object that, let's give it a name. I'm going to call it this. we'll see. This is just vacuum. We'll come back to this. So this is a family of correlation functions I constructed out of correlation functions for all n larger than positive integer n. Yeah. You can analytically continue this to this range. And we'll see that it's monotonic. Well, we argued that it's non-negative, and we'll see that it's monotonic. This has a name. This we're going to relate it to a. This is actually we're going to relate this to a quantity in quantum information theory. It's called Sandwich-Renyi divergences. So it's particular quantum information quantity we're going to construct that is particularly this correlator in quantum field theory, and it's monotonic. One comment is that this is to be understood, as we'll argue, as a Renyi family for relative entropy. Relative entropy is famously UV finite, so it doesn't suffer from ultraviolet divergences. And it's very suggestive. The fact that this is a one-sheeted correlator, not like Renyi entropy that's in-sheeted correlator, it's very suggestive of the fact that this might actually have a UV finite definition in quantum field theory using modular theory. And this is what precisely we're going to find. All right, so this is the end of part 1. Are there questions? OK.
Sorry, at the moment it doesn't look much like an entropic quantity.
Second part is about that.
And the correlation functions, of course, are well defined, right? So
Yeah.
I guess it's clear it's coming.
Yeah, yeah. So part 2. Sorry? Again, I have to say, I'm just showing you a proof of principle as how to, an instance where you could use modular theory to extract non-trivial constraints. I'm not saying that this is the most interesting constraint. So now consider Euclidean path integrals, and what we usually do in the case that we're just talking about density matrices quantum field theory, and we're a little bit sloppy about cutoff or divergences. So let's take Rendular space.
Sorry to bring you back to this, but just to understand, this is going to be, can you just explain once more what precisely is going to be a Sandwich-Renyi divergence?
That's what I'm going to say right now. Yeah, so here I just define it. I give it a name. I define it in terms of correlation functions.
But at what values of, I mean, these correlations.
So what's in there? What has gone into it? There's a choice of phi. There's a choice of x. And there's a choice of a. Yep. So I'm going to draw all pictures in 2 dimensions, but this really applies in arbitrary dimensions. And you could replace all these del x's and del u's I was talking about with shifts on a null line if you're careful with the fact that that's not a topological charge. But that's a subtle comment. So usually what we do is that we take the Euclidean plane, and to find the density matrix of a region A, we perform a path integral around this. And if you insert no operators, you get the vacuum density matrix of A. So I have in mind Rendular space for simplicity. Now, consider a state that is created by the action of an operator phi here that's inserted. This is at point 0. This is positive line, say. A is positive line. It's inserted at point minus x and at some distance a over 2 from this. So if I perform a path integral from minus infinity to this line, I get a state. Let's call that phi. And if I perform the path integral around this, I get the reduced density matrix. Well, let's call it rho so that people don't get confused. And this state. So it's clear already that making the region larger or smaller corresponds to changing the value of x. So if I make x smaller, corresponds to making the region larger. Or if I actually send x to some, move x by some del u in null direction, I'm deforming the region in null direction. So now consider the following path integral. Same setup, phi star, distance a, distance x, but just a wedge, a slice of pizza with angle 2 pi over n. And I'm just going to assume that x is large enough so that these guys don't go outside. So what is this path integral? What operator corresponds to this path integral? Well, the answer is very simple. This operator is the same as this with wedges of vacuum removed from it. So what is this operator? This is rho of a, sigma of a to the power of 1 minus n over 2n, which is a negative power. That's what it means to remove the edge. Good? Is this clear? So it's already clear that if I just take this guy and patch it n times, as I go around the circle, I get the following correlator. Well, yeah, I get phi I star. And the normalization of the density matrix tells you to divide it by phi star to the power of n. What is this? This is precisely this correlation function I constructed here. So it's 2 pi n as you go around the circle. All right, so if I look at this quantity and write it in terms of this, it's just a rewriting. I find what I defined before in terms of density matrices when they exist. It's the following object. This is a well-known quantity in quantum information theory called the Sandwich-Renyi divergences. Famously, is non-negative and monotonic in X, as you perform partial trace on both of these guys. But we'll actually show this, or maybe argue, given the amount of time we have. So again, this guy is defined in the range half to infinity. It's not very obvious, but I'm just going to code this. In the limit of n going to 1, this becomes relative entropy. So in that sense, it's a Renyi family for relative entropy. In the limit of n as n becomes half, which is the lower part of the limit, this is related to, it's actually e2 minus half fidelity, another measure that we use in quantum information theory a lot, and we love fidelity of the two states. No, I think that's correct. Sorry? Yeah, because this is I think, OK, so let me not, it's just it's related to fidelity. I don't want to. So fidelity is actually this, right? Yeah, OK, good. You're right. Sorry. I meant to say this. I meant to say e to minus half s 2 or half. I'm not 2 or half s half of rho sigma. Anyway, it's related to fidelity. It's related to fidelity. Up to factors of 2 half exponentials, logarithms. It's related to fidelity. I can if I have time at the end. Let me finish this story, but I'm more than happy to comment on them. There's a discussion of that in the paper. Oh, OK. All right, so let's do one little thing. Let's start with this guy and massage it and write it in a suggestive way that we're going to use later in the part 3 that's going to be more appropriate for modular theory. So how are we going to do this? First of all, remember the definition of a p-norm. So if you have a matrix, the p-norm of a matrix is the trace of a to the power of p, to the power of 1 over p. So from that, I learned that I can write this also as a p-norm. So it becomes n log of the p-norm of this guy, the n-norm of this guy, sorry. Now, this operator looks like x dagger x, but the n-norm of this is also equal to the n-norm of this guy, just because n-norms are unitarily invariant. So I can write this as n over n minus 1 logarithm of rho half n. Sorry. Now let's do one last redefinition, which is to just define this to be 1 over alpha. It's just a reparameterization of what, oh, sorry. No, I don't want to write it that way. This is 1 over alpha, so that this becomes log of rho half. Oh, actually, no, sorry. Yeah, I think that's not what I want to write. So this becomes sigma of alpha over 2 sigma of alpha over 2 rho. No, actually, that's correct. Yeah, that's correct. Well, at first it might look, why am I doing this change of parameters? But it's more helpful. Then what it does is that now alpha is in the range -1 to 1. So here I'm going to use something that unfortunately I will not explain, but it's a famous result property of p-norms, which is the so-called Holder inequality. So let's look at trace of AC, norm of this guy. Yeah, so this is clearly less than AC 1 norm, right? That's obvious. And the statement of Holder inequality is that for P and Q satisfying this relation, this inequality holds. This is Holder's inequality. Unfortunately, I will not have time to justify it. You can find it on Wikipedia, read about it. OK. So in particular, this formula suggests that I can write down the p-norm of a matrix as the supremum over all What does this mean? It means that if you take a supremum over here, this equality is the saturation of this is achieved, saturation of this is also achieved, right? So after all this business, after the dust settles down, you end up with the following object. It's just a redefinition of what we had, what we started with. This guy becomes a 1 over alpha supremum of log. Oh, actually, sorry, I should mention this. For this story to hold, it's important that P and Q are in 1 to infinity, for which I have to restrict myself to the case alpha is larger or equal than 0. Trace of. So now, this condition, what is this condition? Let's call this chi instead of c. This is the fact that trace of chi to the power of q is equal to 1. So this could be written, well, actually, maybe I want to, well, sorry, I think I shouldn't have changed the name of it. It could be written in the following way. It could be written as rho half sigma minus alpha rho half. All right, this is the final form. I'll not change this anymore. So after some algebra, it's rather trivial algebra. This quantity, so what we start with this quantity. Thanks. We massaged it into this quantity, and we wrote it in this language. So I'm now at the end of part 2 of my talk, because this quantity is very obvious to generalize to. It's easy to generalize this in modular theory and see what this guy is. Are there questions so far?
Can you comment on the case where x is small?
What is?
When x is small?
X is small.
Presumably the second
So-
inequality got the sign change.
So here, sorry, the second inequality.
So I presume there's an x where it becomes a triangle, for example, in the
Um,
picture. Yeah.
oh, okay, that picture.
There's an x where it becomes a triangle. And when I mean x is small, I mean x smaller than that.
Oh, you mean phi and phi tilde go outside of 2 pi over n wedge? Okay, so let's first not talk about that, and we'll come back to that. It's actually, it doesn't really matter, but it requires, I have to tell you a little bit more about sophisticated ways of dealing with this. But actually, one thing that's interesting is that, so I use this heuristic picture to argue for this quantity that at the end I'm going to define without really needing to talk about correlation functions like this. So the final quantity we're going to define for the cases, for certain cases, it will become this correlation function, but it has a more general form. But that's a very good question. I think that confused me a while back when I was looking at these correlators. All right. So if there are no more questions, the last part of the talk is to find this object in modular theory and see it's monotonic in a very trivial way, just by construction it's monotonic. And I'll comment more on how to use modular theory as a systematic way to find inequalities of this type. So Tom Faulkner did a really good, included a really good review of some basics of modular theory. So I will not review much, but I'll just say a minimum that is going to be important for me. I'm talking about the Rindler wedge for simplicity. So this is the region A. There is an algebra of region A associated with it. And every time I write little a, I mean a bounded operator in this algebra. There is a vacuum state omega that describes the state, global state. So I can think of a map from the local algebra to expectation values. What is this map? It's basically this map, right? In quantum field theory. And in the case that I have finite quantum systems, if I have some state omega, which is chosen such that the reduced density matrices are full rank, then the same quantity could be expressed in terms of some, sigma, I call this sigma, some positive operator on the, so this is left, the left side. So this equality is a thing that we do not have. This we do not have in quantum field theory. There is no, because there is no the full Hilbert space, the global Hilbert space, in the case of finite quantum systems, or left or right, has a tensor product structure. But here we do not have that. We can still talk about this. This is the some map from the algebra to expectation values. It just doesn't have a representation in terms of a density matrix. So in the formula we're going to write down, we're not going to use any density matrices because they're not allowed. Now, Tom defined this in his talk, so that makes my life easier. The following object, take two states of quantum field theory, omega and phi. I have to warn you, unfortunately, I'm very used to a notation which is the opposite of Tom. So I'll define it. These are, these are star algebras that we were talking about. What does that mean? It means that to every operator A corresponds an A dagger. So I'm given two states. I'm given A and A dagger. I can define an operator that maps this guy to this guy. Now, the fact that the state is cyclic and separating is the statement that this approximates any state arbitrarily well. which means that if I could close this if I close this operator, so which means that this operator, sorry, this equation defines an operator that after closing is a full definition. So I can close this and look at its norm. Its action, yeah, the density fine, sorry. That's what I meant. So I can define, so now here I'm replacing this guy with this closure. But this is what the operator is. This is a so-called relative modular operator. I use very little structure. Basically, any choice of two states and a region, because the operator were chosen from a region. For any choice of any two states and then a region, I can define this object. Well, of course, I assume that this state is cyclic and separating. I don't have to, but it makes my life much easier. So let's assume that. Now, this operator has a property. So there's an index of the region that this guy carries, A. Now consider the following setup. Consider consider the algebra of region A and the algebra of well, actually, I want B to be larger. A to be inside B. So the algebra of A is inside the algebra of B. Then there is, you could use from the very first definition, and this simple fact, you can show that this modular operator is monotonic. So let me write it this way. I'll explain what this equation means. I'll not prove this. Or for the proof, to see proof of this, you can see Edwards' notes or some earlier references in the case of finite quantum systems. So this is an inequality that holds. You might complain that these operators are unbounded. Oh, by the way, I should have said these are unbounded operators. Let me actually give you some intuition before actually jumping ahead. So you might ask, what is this operator in the finite quantum systems? So there are the choice of two states. This operator is nothing but rho of A tensor sigma of A complement, where sigma of A is defined from partial trace of, let me write it down. So sigma of A is a partial trace of omega omega, and rho of A trace of A complement. Oh, yes, thanks, indeed. So this is what the operator is. It's not something crazy. Thanks. So what I mean by the monotonicity of this operator inequality is that for any beta larger than 0, if I look at this operator, this operator is bounded and defined everywhere. It's actually defined everywhere in the Hilbert space. Why is it bounded? Because it's a bounded function of an operator that's unbounded, so it has to be bounded. Therefore, you have this inequality as an operator inequality, meaning that if you evaluate this both sides in arbitrary states, so if you look at, so if you put some psi here, psi here, this is an equation for arbitrary psi. This is the so-called monotonicity of relative modular operator. One more comment is that, so the normal modular operator is when you pick both states to be the same. So the modular operator you've heard of is when you pick both of the states to be the same. Monotonicity of modular operator, where both states are the same, has been used to derive ANEC. And now we're going to be using monotonicity of this object with more than one state in it. So what are we going to do? Again, these are famous expressions, but so this is a positive operator, right? So I can use I can do a spectral decomposition of it and define delta to a power of minus omega. I'm just suppressing all these indices for now. Sorry. D beta, beta minus alpha. And then there's an analogous expression for when this is positive. So this is, I picked alpha. Oh, sorry, I should have said this. I picked alpha to be between 0 and 1. And there's an analogous statement for when alpha is positive. There's a sign that's different here, and then there's a shift of 1 over beta. So basically what you get is that for the range of alpha in between minus 1 and 1, you get sine of alpha of A, sine of alpha, psi. Well, maybe I should have used flipped psi and phi. I think that's a better, it's adapted better to my notation later. So this is the inequality you find. Good. All right, so now let's do the following thing. Let's just plug in the expression that we found, I claim for the relative modular operator in here. So what is this? This is phi sigma to a power of, oh, sorry, I want omega and psi. Because this holds for any two states with whatever. I'm going to pick this particular order. Alpha, phi. If you're familiar or comfortable with tensor diagrams, what this picture is telling you is this is a vector of a bipartite system. This is sigma to the power of minus alpha. This is psi to the power of alpha. This whole thing is really trace of psi to the power of alpha, sig phi, rho half, sigma minus alpha, rho half. This should be familiar from here. This is the same expression with chi and psi swap. So the last step is basically writing the very definition of the Sandwich-Renyi. So yeah. So when sorry. Let me explain. So phi is a state, the global state of a theory, right? So think of it as, let's for simplicity take it to be cyclic and separating. Then I can prepare the state by, or I can associate some density matrix canonically with it, acting on a maximally unnormalized maximal entangled state in finite dimensional systems. Right? So so this is the expression that holds in continuum theory. What I'm writing here is analog in finite quantum systems. In finite quantum systems, if I pick this guy to be cyclic and separating, I can always write state phi as some density matrix acting on this. Yes, precisely. Of course, this basis is a bit. That's right. So I guess I jumped over a bunch of steps. But yeah, given that I'm running out of time, I just want to write down the expression. So omega psi minus alpha phi, when alpha is between 0 and 1, and when alpha is between minus 1 and 1, this supremum becomes the infimum. This quantity, sorry, minus 1. Correct. Thank you.
Supremum over what?
Supremum over all states psi.
All states.
Same here that I had supremum over all chi's, density matrices chi. So maybe I should call this same thing. Right? So now this is the object that hopefully I argued becomes the Sandwich-Renyi divergences. Now you could ask whether it's monotonic. Well, I just told you that this object, this operator is monotonic. This is just a particular matrix element of it, and I'm taking supremum over it. So it's going to be monotonic. So this quantity, monotonicity of this quantity follows trivially from monotonicity of relative modular operator. All right, so I'm done with my story. I just have a few comments. How much time do I have? All right, just like give me 1 minute. That's it. So this quantity is monotonic, and when alpha becomes 0, so alpha is 1 over 1 minus 1 over n in the previous notation. So that's when n goes to 1, the Renyi parameter goes to 1. That's when I claim it becomes relative entropy. When n goes to 1, this is just monotonicity of relative entropy that we proved. If you remember from Tom Faulkner's talk, QNEC is this statement. And the conjecture that I talked about at the beginning of the talk was this statement. The conjecture holds trivially for the case of n equal 2, as we just proved, because it's a positive operator. You take it to an arbitrary positive operator, it holds. But for larger than n larger than 2, it's a generalization of QNEC. And I've looked at all the examples I know. It holds. But it would be interesting to know whether it holds in full generality. And yeah, that's it. Thank you.